Okay, so it's 2 o'clock. Suggest we start this webinar. Today we have a use case, a very cool use case of using Kubernetes and containers for science and analysis reproducibility. We have Diego Rodriguez from the REANA team at CERN talking about it. We'll do this as usual. Diego will give his presentation and a cool demo. If you have any questions during the presentation, feel free to drop your question on the Q&A box, and we'll pick it up either during the talk or at the end. Otherwise, if you can also use the chat system if you prefer. So I'll pass to Diego. And thanks for presenting, Diego.
Thanks, Ricardo. So my name is Diego. Again, I say I'm from the IT department. Just to highlight, I'm a software engineer and part of the REANA team, and I will be talking about analysis reproducibility with REANA on Kubernetes. And I will be talking on behalf of my whole team. So first and foremost, I would like to highlight why do we do this. So it's simple. Half of the researchers cannot reproduce their own research. It's simple, but it has a huge impact. We can see it in this Nature magazine survey, where scientists from different disciplines have reported that they fail not only to reproduce their own research, but not someone else's research, but also their own. And this becomes really a big problem when you combine it with a high turnover. This is something that happens at CERN. We have an example here. The first physics paper 10 years ago of the DCB experiment. From the original author list, half of them are not with us anymore at CERN. And yeah, when we try to tackle this problem, at the beginning it might seem simple, just combining a few pieces and adding new parameters to an analysis and try to get a result. But this most of the time is not so easy. We get down the rabbit hole and we discover that there are many subtleties that were not thought of that would break in the future or be a problem. So if I am a researcher and I would like to make my analysis reproducible, I would need to answer a few questions at least. I would need to know where my data is. It's not enough if I have it in some hard disk that then it will be broken. I have it in some central service that is it's stable, it's battle tested, such as EOS. Or I need to know how where my code is, the code that uses this data. Using Git is part of every physicist workflow, almost every physicist workflow nowadays. And we have stable services at CERN. We have a Gitlab, and it has been battle tested. Then we need to know as well where the environment is or what the environment is. I might have a different version of Linux or Mac OS, different system library that in 1 year got updated, and I have no clue that it got updated, and now my analysis breaks, and I don't know why. So all of this needs to be encapsulated. So as I mentioned, for the first two questions, we have well-established solutions at CERN that have been battle tested. For the environment, we are seeing that, for instance, Atlas now starts to containerize their environments in Docker images as well as CMS, and they are using central Docker registries to keep those versions and have like future versions and also backward compatibility with old ones, so analysis can still run. So if one would need a recipe for reproducibility, we have kind of answered the first three questions, but we are missing the last piece, which is this knowledge and these computational recipes that analysts and physicists were using to put together this data code and environment and produce a scientific output. And without those, we cannot really reproduce. So when we achieve to store this information and make it runnable, we can achieve this reproducibility goal. So an overview of what REANA tries to do is to try to get all those existing services that are well established at CERN and putting them together in order to allow this recipe to be reproduced. So we have different storage backends, we have different EOS, FFS, we have different compute backends that maybe not always are for, I need one because it's faster than other, but also this provides a very easy way, as we will see later, to prove that some scientific output can be produced in different compute environments, not only on Condor, but also works on Kubernetes, and we have the same output. And this makes the analysis not only reproducible, but also more robust. And then the last one is the workflow languages, which is the less explored one, and it's the one that needs to get well established, and it covers what languages are used to specify those steps, those recipes. And those languages are runnable like computational recipes, and go from simple pipelines that are sequential to complex MapReduce parallel operations. And last, we have environments, different environments, Docker, Singularity, CPMFS. So as I mentioned, it's key to have integrations with other systems, and also integrations on the with the access restriction, because it's important for the collaborations to keep their analysis behind like private access for until they publish them. So we have possibility to use private Gitlab images to access to stage in and stage out content data from EOS using Kerberos, and accessing the grid using Von's proxy certificates. So until now, I've been only talking on what we are trying to do. Now we'll go on a more practical demo on how things look, how the REANA user interface looks, how the command line interface looks. We'll go through a simple physics model analysis, and we'll see how the Gitlab integration works. And along this way, we'll observe how the REANA architecture looks like in Kubernetes, and how it evolves during the execution of user workflows. And for you to have an understanding of how it will be looking like, you will be seeing in black the REANA CLI, which means this is the end user view. So if you're an end user, you don't care about the blue part. Well, maybe for curiosity, but you don't need to know this complexity. And if you're an admin and you're curious, you can see the blue part. So in order to see to do the demo, we'll use an existing example. It's a model physics analysis that we have. It's a simple roofit, and it's hosted on GitLab. So this contains some source code and some information that we need for the analysis to run. And we have a extensive README answering the questions that I just mentioned before. So this analysis doesn't have input data. We just simplify that part, but we could have it as well. Then has some code, and a part of the code generates some signal and background data, which ends up being a root file. And then there is a feed data root macro that will output a plot. So this code is part of the repository. Then we need some environment where these root macros can be run. And this is an environment called REANA root 6 that has root 6 runtime. And this is something that we maintain together with physicists, and offers an environment for root 6. As simple as that. And then regarding the workflow, it's very straightforward because it's like a model example to get started. And it has just two simple steps. And as I mentioned before, the gen data macro generates a root file, and then the feed data just process it and feeds this data and generates a plot. It's two commands, but we can very quickly imagine how this can be growing and become complicated if an analysis is more complicated than just doing this toy example. And the output would look like this. It's just a plot. And then answering the questions wouldn't be enough. We need to document it, right? So for that, we have a file in this repository, which is what most of the analysis don't have. And it's this REANA YAML that has metadata about the analysis. But this is not only metadata, it's actually a runnable recipe. So here we have what our input data is, what our input parameters are, for instance, number of events, what the data is, the path to the file. And then we have the steps that need to be taken. As we saw before, it's a couple of commands, and then we document what the output is. So this is important because we put everything together. We answer the questions and then we put it together, and actually this can be rerun. And this is what it makes it powerful, because before we didn't know how to put things together. Even though this is a simple example, when it grows, it's not straightforward. So how does this practically look? How can we use this? So first of all, we will need to head to a REANA instance. And here, when you enter for the first time to a REANA instance, I'm entering production, although we'll do the demo in REANA QA, for you to see that we have some help in the beginning. So it tells you what are the steps that you need to do to get the REANA CLI working on LX Plus. But you could install it in your laptop as well. But I will do it in LX Plus since I'm at CERN. So basically, I will be sourcing a virtual environment where REANA client is. And I see that I have REANA client installed, and I see that I'm authenticated already. However, if you do it, you will have to first, let's go already to QA, which is the view that we will have during the demo. You will log in there, and this is using the CERN single sign-on, and you can go to your profile and get your connection here. Your connection details. Okay, so we would have it here, and you would copy paste it and add it to your shell environment. And once you have done this, you will be able to do this REANA client ping. And the REANA QA, it's a Kubernetes cluster, which you can see here has a couple of nodes only. It's our quality assurance cluster, so one can see it. Here that it doesn't have many nodes. And it has the following pods running inside. So what is in here? We have different components that compose the architecture of REANA, which is a cache, it's a Redis service, a message broker, which is a RabbitMQ, which we use for queuing mechanisms and message passing. So those are very plain. They are just using the Docker images as they are. And then our actual code that we are developing is the REANA server, which offers a REST API and authentication. And here we have a cron job, the REANA system status, which is executed every day. And it's giving a status report of what the system looks like, if it's healthy, if it's not healthy, and all of like useful information for an admin to do like administrative work. Then we have the REANA UI, which is the next service that is serving the React interface, and a workflow controller, which is another microservice that has that is the one that is in charge of managing workflows, creating them, creating workspaces, managing the life cycle of a workflow. So that's from the Kubernetes side. And right now we are ready because we have this REANA YAML here, the one we saw in GitLab, with all these files, parameters, steps. We are ready to run, and we'll call it webinar demo, for instance. And we can observe what's actually happening. So on the Kubernetes side, there is a new component that wasn't there before that we can see. And we are gonna see what is actually inside this. We'll see. I'm gonna monitor this as well, so you see what happens afterwards. So inside this new component, which is a REANA run batch, there are two containers. One is in charge of interpreting the workflow specification. So in this case, it just reads two sequential steps, but in a very complex step, and in a very complex analysis, as we will see later, this can become like many steps. So it grows in complexity. And then we have the job controller, which is in charge of submitting jobs to compute backends. So if you notice in this REANA YAML, there is nothing that specifies here where to run these steps. There is nothing that says Kubernetes or htcond or whatsoever. So by default, REANA runs on Kubernetes. And that's why we see that there is a run job with this ID that run here. So since we didn't specify, runs by default on Kubernetes, and this is using the Kubernetes API for jobs, and we are using it from Python. So as a user, how does this look like? We can see the status of a workflow, and here we see that it's finished. And then if it's finished, we can see the workspace of this workflow. The workspace is just a scratch space that is living in CFFS and is created on demand for every workflow. So here we have the intermediate steps, outputs, the root file that was generated by GenData, and then the final plot, which if we want, we can download and do something with it locally. And last but not least, if something would go wrong, we would see the logs of the workflow. And something interesting here for someone that is doing running real life analysis is that we have the logs of the workflow engine. In this part, you will get syntax errors if you are writing wrong the workflow specification or get information of what is happening with the workflow. And then down here, you will see the logs for every job that is being executed out from this big workflow. And something to highlight as well is that these logs belong here always have the same format, and doesn't matter which compute backend you use. So it's a unified user interface for accessing logs. And this is something that we can also see in the user interface. We can see all the steps and all the logs. This is something that we did in the CLI, but it's much easier to use. Here we can see that it was a Kubernetes job. We can see which environment was used and the command that was issued. And also we can inspect the workspace and actually see the plot. And also see what our specification was. So until now, we took this example, we cloned it locally, and we ran it with the REANA client CLI. But if I'm a physicist and I have my workflow on GitLab, there are other options for me to execute this analysis, and this is through the GitLab integration. And for that, one just have to go to the profile and connect GitLab with REANA. Just basically clicking here, going through a node to workflow, and just authorizing REANA to read the GitLab API and read your all your repositories. So you would accept it, and what you get when you get back is that you get a list of all your repositories. And here we see that we have the root 6 roofit example, which is the one that we have in all the time, and you just have to come here and click to activate the integration between this repository and REANA. And what does this mean actually in reality? So it just means that now REANA is it's doing the CI part of your, it's acting as a CI system for your GitLab repository. So basically, if someone comes here and wants to change the number of events from 20,000 to 80,000, and the person commits like update events, commit this to master. It's my own repo. We can do that. So we get back here. We have a new commit, which effectively changes this line in the REANA YAML. But in real life, physicists most probably would come here and change something in the feed data because the feed is not working. So you have to change the line here. Again, this would be just a change in the repository, which will then on the REANA side trigger a workflow run. And how is this working is that now we have the same as we had before. There is the execution. We see that the feed data still didn't get executed. We had the logs for gen data. Here we see that it's a Kubernetes job. It used the root 6. It's the same analysis as we ran with REANA client. And after some time, we see that it succeeded. We get exactly the same logs. It was run the same way, but through GitLab. And how does this translate in the GitLab UI? So basically, if one refreshes this page, now you get a commit status on your commit, which basically says this commit is good and doesn't break your code. And this is acting as a CI system for your GitLab repository. And this is good because it's integrated already with all the features that GitLab has. For instance, email notifications. If a build breaks, you get an email notification if it's on master. And all these kind of good things also allowing to merge a merge request. You will get approved also from the REANA side. And if we get back to what's happening in Kubernetes, here we see that a lot of things were going on. All these jobs have been running, but if we just check the pods that are running right now, there is nothing anymore. So this is because we are running everything that belongs to our users as Kubernetes jobs, from the workflow interpretation to the job submission to the jobs in some cases when we don't use the external compute packets. And this allows us to have really low usage of our cluster and only grow when there is actual traffic. So this was the walkthrough on the simple example and the GitLab integration. I would like to have a word now on the declarative approach of REANA. And we can see it. Here we have the simple REANA YAML we have been seeing on the example, but now it has a new line, which is basically saying run on HT Condor. So this on the REANA UI, if we go back, I have something that I ran this morning, an HT Condor. This I'm not running now because it takes a bit more time, but basically you can see that this was run on HD Condor. It used the Docker image, and we get exactly the same logs. And we see files here coming from the like HD Condor logs, because this is using HD Condor. And we finally get the same plot, but from a different compute backend. And all the user, let's go back to the slide, all the user had to do is to change the line in this declarative REANA YAML. And then this REANA, here we can see on the right, who deals with the complexity of interfacing with external compute backends. In this case, we are interfacing to Condor. Then a word on scalability. We have a beyond standard model searches example, and with this we have been improving the scalability of the solution, and this is thanks to all the advances that have been done on the cloud containers at CERN and the Kubernetes through Magnum, and also we can make it easy to be run by physicists through the Gitlab integration, because we have this service well established and used by physicists. And this is not anymore a toy example. I have it run here. You see that it has 60 plus steps. One can see the logs for all these steps. It was run on the Kubernetes backend, and uses, well, this step uses the VSM search one. Actually, all the steps are using this, but some of them use root, as we can see here. You will see updated this information. And you could also have that you run a step that runs on SD Condor. You could also do that. So going back to the slides, we, thanks to all of this work done together between different IT services and the REANA team, we have achieved to get working examples with every main experiment. And if you have any analysis that need to be made reproducible, please contact us, because we can enlarge this list and get more pilot examples. And to do so, you just have to type reana.send.ch in your browser. You will get the user interface that we just saw. When you are first logging in, you will get information on how to get the REANA client and interact with the system. And if you want to install it on premises, you can also install it with Helm. We have Helm charts available for the installation, and you can find more information in the slides, clicking on the links. And yeah, last slide is dedicated as just please join us. You have the REANA CERN link, the service, you have our documentation, and you can get in touch with us through any of our communication channels. And also on GitHub, because we have quite an open community there. We are not working, we're working with physicists, but not only. We also have contributions from life sciences, bioinformatics, and also from astronomer community. And you can contribute not only infrastructure code, but also environments, like Docker images and actual, the Docker images that will be used for analysis, or analysis of yours that you want to make reproducible. So the possibilities are endless. That's it. Ready for the Q&A.
Cool. Thanks a lot, Diego. This is pretty awesome. Nice demo. I don't know if anyone has a question right now. Feel free to start typing, or just raise your hand, and I'll try to give you voice as well. I have a couple of questions, so maybe I can start, and then people can see if they come up with theirs. You mentioned about resource usage, and like when you're not running the workflows, then there's not a lot of load in the system. Do you have cluster auto scaling enabled, and do you have some experience with this?
No, we don't have it enabled right now, but it's something that we would like to explore. Since until right now, we never had the need. We had a big workshop early in the year, and our current cluster of 10 nodes, I believe so, of X large machines could endure 30 users parallel running BSM workflows, like the one that you saw with many nodes. So once we hit the problem, we will definitely be interested in the autoscaling.
Okay. Um, the other question I had was like one big part of this is the containerization of the user's code and data. Is it something that is kind of like standard, you would say, in at least in the high energy physics community, or like was there resistance? What are the problems people have? Things like this. What would you say?
So I think traditionally there was always an effort before with VMs, DBMFS. It's just that the technology is changing. And as you saw before in the slide, uh, I flashed in this one that there are already central images for Atlas and CMS. So I would say that traditionally there has been a lot of good work done, and now physicists are changing to the next level with containerization that will enable reproducibility more easily. So I don't know what's happening in the other two collaborations, but I can say that in Atlas and CMS, this is already happening and being used.
Okay. I don't see any other hand raised or question coming. I think it was a nice and clear presentation. um, so if not, then Diego, thanks again for for the cool presentation. If anyone wants to follow up with Diego, you know where he is at CERN. Otherwise, maybe you can put again the page with the contacts. And yeah, just reach out if you want to know more about how they use Kubernetes or about the system.